Welcome back, students. Today we will going to do magnetic field due to a circular coil on its axis. Okay, say to start with, let me take this way. Okay, let us take x-axis, y-axis, z-axis. This is a convention. Okay, x, y and z-axis. Z-axis I cannot show it. All right, let me consider a circular loop. Okay, and say the circular loop is in the x. Let it be existing in the YZ plane. Okay, YZ plane. When I say YZ is, this is Y and this is Z, right? Isn't it? This is Y, this is Z. See, this is Y and this is Z, and the circular loop is existing in the YZ plane. All right. Okay, then the axis perpendicular to it is what? This is the x-axis. All right. Okay, this is the one what I meant to say. All right. Now YZ plane I cannot show it here. All right, so I'm showing it by this means. Okay, let me make it this one. Let me make it smaller. Okay, this is x, y and z. All right. Now let's say the current is going through it in the clock sense. Okay, clock sense. Okay. Now say this is the radius of the loop. This is only given. This is given and the current is given. All right. Now let us find out. Okay, let us find out the magnetic field on the axis of the loop, on the axis anywhere. All right, say here, say this point is P. All right. Okay, now from the center the distance, say it is x. The given magnetic field due to a circular coil, it is given, the radius is given A. This is what? This is radius. What are the quantities given? Radius is given. So on its axis, say any distance x. All right. And definitely there have to be current, because if no current, there is no magnetic field. Right or not? Okay. Current is necessary to have the magnetic field in its surrounding. Right. There will be magnetic field here, there will be magnetic field here, there will be magnetic field in the surrounding. But we are not finding the magnetic field anywhere. We are just finding the magnetic field on the axis of the loop. Understood? Okay, fine. Now, we know how we can find out the magnetic field. Our means to find out the magnetic field is the Biot-Savart law, right? And what is the Biot-Savart law? Biot-Savart law is mu 0 4 pi I. We have to choose the elemental section. Let me choose the elemental section dl. All right. Now, if the current is going this, what is the direction of dl? This is the direction of dl. Direction of dl is given by the direction of current. This is the direction of dl. Yes or no? All right. Right? Current direction. I have chosen, this is the elemental section, this small section. The direction of current at this point is along here. The direction, if I choose this elemental section, what is the direction of dl? This is the section. If I choose dl this way, what is the direction of dl? This one. The direction of dl is given as the direction of the current, right? Okay, now this is what? The direction of magnetic field is across dl cross r and r cube. This is the Biot-Savart law, and remember, Biot-Savart law is valid only for the elemental section. All these things we know it, right? Now you tell me, what is r? R is the distance of the elemental section from where to find out this. That means what? This is the elemental section and what is the distance? This is R. Right or not? Okay. Now, what is the direction? What is the angle between DL and R? See, this picture is not a two-dimensional picture. This is a three-dimensional picture. What I was saying, the loop is in the YZ plane. This is Y, this is Z, right? The loop is like this, right? And how the current is going? The current is going clock-sense, right? The current is going clock-sense. And where the axis is lying? The axis is lying in the x-axis. Imagine, this is three-dimensional. Okay, fine or not? Now, if I take this bangle as the loop and this is the one. Now the current is going in this one. I took the elemental section, this one, the small one. What is the direction of DL? This is the direction of DL across here. This is the direction of DL, right? Now the axis, this is the one, right? What is the, this is what? R, right or not? Now what is the angle between DL and R? See, DL, right? This is, isn't it tangent? And this is what? R, right? What is the angle between DL and R? Isn't it 90 degree? Yes? From the figure we cannot know it, but when we see it in reality, it is this, right or not? Fine, this is R. Every time the angle is 90 degree. Okay, so DL and R. If I take this section also, because the current, if I take, say, this section, okay, what is the direction of current? This is the direction of current. That means this is the direction of DL, right? This is the direction of DL. Now this, isn't it tangent? So the tangent always make how much with the radius? This is 90 degree, right? So this angle is 90 degree, right? Okay. Alright, so this is what? Mu 0 I 4 pi DL R sine of 90 degree. This is R cube and R cube, sorry, this will be R will, the square will remain, right? Now coming about what is the direction of dB. What is the direction of dB? This is, the current is going what? Clock direction, clockwise, right? This is the direction of DL and R is somewhere like this. R is somewhere like this, right? Now what is the direction of dB? The direction of dB is, can be known from the screw rule, right? You make the rotation from DL to R. In what direction the screw goes, that is the direction of dB. Yes or no? Screw rule will give you much accurate result than the Fleming right hand thumb rule. Okay, more than the thumb rule, screw will give you. Now see, this is the direction of DL and this is the direction of DR. This is something, R is not straight because it's something like this, right? Fine or no? This is DL. Now this is, make the rotation, okay? What, where it goes? Is it goes straight? No, R is like this. It goes this way. So what is the direction? dB, like this. Imagine, student, you need to imagine, there is no other alternative. See, DL is going this way. R is like this. What is the direction of dB? DL to R, you make the rotation. Now what it goes? It goes like this. This is the direction of dB. Now, so what is the direction of dB? This is the direction of dB. Okay, fine or not? Now one more thing. See, dB is perpendicular to DL and perpendicular to R, right? So this angle have to be what? 90 degree always. Okay, fine. Now Okay, so I did for one elemental section and I found that the direction of dl is somewhere down. Okay, this way at this point. All right, now if the current, let's do for one more. All right, let's do diametrically opposite here. Diametrically opposite. Now what is the direction of dl? Somewhere here, right or not? Right, this is the direction of dl, right? Now what is the angle? R. Is it obtuse angle? No, this is again 90 degrees. See, that's why I'm saying this is a two-dimensional picture, but in actual it is not a two-dimensional picture. This is a three-dimensional case. Like say, the current was going this way. That means here it was coming this way, right? The current is coming this way, right? So this is the direction of dl. How the R is like this, right? Fine or not? Isn't it? What is still the angle? Still the angle is 90 degree, right or not? Okay. Now diametrically, here I have taken dl previously. Now I'm taking this. But dl direction was like this as the current is coming. Here as the current is coming like this. Okay. Fine or not? Alright. Now what is the direction of magnetic field due to this elemental section? Now magnetic field goes here. This is dl, right? I need to make the rotation from where? dl to r. Now r is what? This way, right? I think dl direction is, if I use the thumb rule, it will be much convenient, right? Where it goes? It comes up, right? dl goes like this. Now r is this way. Now, sorry. If I make dl this way, then, okay, thumb rule is much convenient, student, for me this time. Okay, so what is that? Isn't it this way? This way? Yes or no? R is like this. See, I'm repeating it. R is not like this. R is something like this. This is the direction of dl, right? This is the direction of dl. Now I'm leaving this one. Something like this. Right? Okay. Now, correct. Going up. But in what plane? Perpendicular to it. Right? Now, perpendicular to it, it has to be, what is dl? db. Coming somewhere here. Yes or no? And this db, okay, is perpendicular to it. Okay, db is perpendicular to r, db is perpendicular to dl. Okay, I have chosen this diametrically opposite. Means if I have chosen this, I have chosen this also, right? Then from both, I have seen that one magnetic field is like this db, another magnetic field is like this db, right? That means the resultant field should be like this. Yes or no? Okay. So what? The magnetic field, the result of magnetic field will be along here. I'm not going to do the mathematics for this. So these 2 dB will give the resultant field here. This is the net field. So the net field will be across the axis towards this direction. Okay, fine. Alright. So we can go okay. So the magnetic field is across here. If I choose for this point also, magnetic field is like this. If I choose for this also, magnetic field is on the axis in one direction. Okay. Now let's take this point, opposite side. I have chosen the right side. Let us choose the left side. Okay. I'm extending it. Okay. See, I'm not going to derive it, but we need to understand it. Because if we don't understand, the next thing we are not going to understand. Let us take any point. Alright. Okay. Now, another point also, let's say any distance, I'm taking it. Okay. I have chosen this distance. And I have chosen the current was going this way. then we have found that the resultant field is like this along here, coming about this point. Okay, magnetic field is like this, current is going this way, it's like this. Make the rotation from DL to R. What is the direction? This is the direction. Means what? This is the direction. The magnetic field direction is like this. Okay. Similarly, if you do for this shape also, the magnetic field will be something like this. Still, what is the resultant field? The resultant field is here, the same direction. Okay, along its axis. Okay, the magnetic field on the axis is directed in one direction only. Okay, along its axis. This is the baseline. Okay, so from all these explanations, now what I am going to tell to you is that one thing. Suppose here is a circular coil in the YZ plane. The current is going in the clock sense. On the axis, if the current is going this way, on the axis, the magnetic field is directed in one direction only. Okay, the magnetic field is going in this direction. Okay, this is a very, very important result. The magnetic field is lying like why it is? Because we have seen that one component, other component will combine, add up, all this. Okay, I'm not going to say anymore. Okay, the magnetic field is directed one way. What about in its vicinity? The magnetic field, see, okay. Now suppose I have other loop, one more loop. I have one more loop. The current is going in the same way. I have another loop. The current is going in the same way. Okay, the current is going in the same way. Now due to this loop at the center, magnetic field is directed this way. Due to another loop also, magnetic field is directed in the same way. Due to another loop also, magnetic field is directed in the same way. That means what? All the magnetic field will get add up. Right or not? Yes? All the magnetic field will get add up because nobody will oppose each other. Okay. Then these, when the loops are made very close to one another, okay, this structure is known as a solenoid. This is known as a solenoid. Solenoid basically what it is? Solenoid is a close rings which are make very close to one another. Okay, like suppose by means of picture you'll see this way, very, very close to one another. Okay, then if the current is going clock sense, the magnetic field due to this at any point in one direction, no, sorry, okay, so this type of helical structure, okay, helical, I must say, this structure is known as a solenoid. Okay, now say the current is going this way. Okay, so this structure is a solenoid. Okay, isn't it, this one, isn't it same as that of this? Here it have to be very close with one another. Okay, now why this solenoid behave as a strong magnet? Why it behave as a strong magnet? The reason I am telling you here. It behave as a strong magnet. It's a very, very strong magnet. Okay. Now why it behave as a strong magnet? Let us see. Due to one ring, just one ring, we have seen on the center, okay, if the current is going this way, okay, the magnetic field is directed along the same direction. The magnetic field is directed along the same direction. Okay, though the intensity of magnetic field will vary, nearer stronger field, farther weaker field. Okay, now So nearer the stronger field. Now what happened? To very close to it, I have put on another ring. Alright. Then the field due to this and the field due to this will get added up, because due to this also the field direction is the same. Right or not? Fine? Okay. The field direction is the same. Alright. So the field will be stronger at the center. Another ring I have put on. Still, magnetic field will be stronger because same direction will get added. In the same direction, same current direction will get added. So what happened at the center? The field is strong. Okay, strong field means what? It behaves as a strong magnet. Okay, then another thing about the solenoid is that outside the field is zero. Inside only there is a magnetic field, but outside there is no magnetic field at all. Why it is? Okay, do you know, due to the straight wire, how the magnetic field is? Concentric circles, right? Right? What to say? Right hand thumb rule, right? This is the one. Now at this section only, if I say, what is the magnetic field? Concentric circles, right? Concentric circles. And then this is the one, how it goes anti-clock, right? It goes anti-clock, right? Even due to this also, what is the direction of current? It goes the same, anti-clock, right? Right? Okay. Now, if you check this one properly, magnetic field due to this and magnetic field due to this, the first circle, if you see, due to this, how it is, right? Due to it, how it's see. How do you see? Right? Fine? Okay. If you check this one, what it is? Isn't it they are cancelling? Now this is true for the whole loop, right? Isn't it? Because one loop after one loop, one after one loop, one after one loop, one after one loop. This effect will cancel another magnetic field. Another magnetic field, they will cancel out each other. So what will be the remain? Center, strong magnetic field, outside zero magnetic field. Okay, so a solenoid is a very important component in magnetism, because solenoid provide a strong field in the center, while rest no magnetic field at all. This one I want to explain it once again to you, because I'm not satisfied. Okay, let's say this is one coil, magnetic field goes this way. Let's say I'm making it little bigger, okay, so the things to be clear. Okay, fine. Current is going at this elemental section. What is the direction of current? What is the direction of magnetic field? Thumb rule, right? So it how can I show it? By means of concentric circles, right? Fine or not? Now what is the direction of it? The direction of it is anti-clock, right? Anti-clock, right? Anti-clock, how can I represent it? Okay, let me just it's anti-clock, right? So this way I can represent it. Fine. Okay, so this is all right. Now similarly for this also, what is the magnetic field still? The magnetic field, one only I'm making it, I'm showing. So okay, if it is going anti-clock, right? Okay, then this is going this way, then this is coming this way, right? Then this is the one. Now if you just see this adjacent one is directed this, one is directed this, and all of them are close with one another, so one will cancel the effect of the other. So on the on the sides, the magnetic field will be zero. The remain is only at the center. This is what solenoid is. Okay, solenoid, how it gives the strong magnetic field. about it. Thank you.